Right gang, welcome to another video here. What we're going to do is follow on from our dynamics topic, and we're going to look at work done in power. Alright, so little guy demonstrating work done in power on the screen, as you can see there, doing some squats. Looks like a guy from work actually. Oh, anyway, right, so work done. Definition of work done: if you move an object by force, it says you have done work. Alright, the amount of work depends on the force applied and the distance moved. Now if you check your formula sheets, you'll be able to see on those formula sheets there's a formula on there for work done. Alright, so get that, check it out. Pause the video if you've not got your formula sheet handy and go and get it. Okay, so work done, the calculation is Fs. F being force, S being distance or displacement, to use proper terminology. So Fs, force times distance or displacement. Alright, now that will lead us to the question, what units do we use for work done? So the actual units would be Newton meters, if we did newtons times distance, Newton meters, but the units we actually use are joules, and the reason we use joules is because we can transfer work, mechanical work, into electrical work and vice versa, and it makes it much easier for us to solve problems when we're using the units of joules there. So that's the more common unit that we use there, joules. Alright, or when you get an answer, if you put a capital G after it, we'll know what you're talking about. Next one, power. So work done is an object. It said we've transferred energy, and you can see that little example on here. So the rate at which energy is transferred is called power, and that might give us a bit of an idea of what information we use when we're calculating power. But if you check your formula sheets, you'll see there's actually two separate mechanical power calculations, and we'll have a little chat about the differences between them in a sec. If you can spot that one, check it out. Right, now what you should find is power is equal to W divided by T. So what we've got here is we've got work divided by T, which is time. Okay, now this is what we call our average power. Alright, but you'll notice on this side we've also got a different formula. We'll pop that around there. So we've got force times velocity. Alright, now that'd be max velocity. So in actual, when we talk about max velocity there, we're actually talking about max power. Okay, so average power is work divided by time. Max power is force times velocity. Now what units have we got for that? So what units do we use? There we go. We can see we can use the either. I'll get rid of that big line for us. There you go. So the actual units that we use when we're talking about power is joules per second, joules second, Newton meters, or watts, which again is the most common one. So when we're talking about calculating our answer for power, it's going to be watts. Again, just to make it easier for us to transfer in between electrical and mechanical power, we're always using the same units at the end. Okay, so that's what your formula sheets look like, and you'll see what power and energy. There's a mechanical power there. I've made it a little bit bigger so we can see those two formulas there. Okay, so let's have a little look at this question. So we've got Max Verstappen enters the pit lane. After applying a braking force of 2,000 newtons, he comes to a complete stop through a distance of 150 meters. It takes approximately 3.2 seconds. Calculate the work done in stopping the car and the power dissipated. Now we'll have a little talk about that word dissipation in a sec, but let's go through this question. So we've got a velocity here. Velocity is equal to 100 kilometers an hour. Now you remember from our previous videos that will allow us to calculate or transfer into meters per second. So we've got 100 divided by 3.6 by simply taking our kilometers an hour and transferring it into meters per second. So we'll get meters per second of 27.7 meters per second. Okay, we've got braking force 2,000 newtons. Force equals 2,000 newtons, or 2 times 10 to the 3 newtons. might make it easier putting it into your calculator. Comes to a complete stop after travelling through a distance of 150 metres. So then we've got distance is 150 metres. Okay, so first calculation, checking our formula sheet. Work done is equal to Fs. Come back to our list. We'll do 2 times 10 to the 3 times S, 150. So work equals, again, stick that in your calculator, although you'll probably be able to do that one in your head, to be honest. And we'll get 300,000 joules. I'll write this in a couple of different ways. Joules, don't forget, or 300 times 10 to the 3 joules. So there's a couple of different ways we can actually calculate that, present that answer. Next one, let's go for power. Again, check your formula sheets, and we'll do both power calculations. We'll do power average, which is equal to work divided by time. I'll go back to that question. Time is 3.2 seconds. Forgot to add that to that slide there. So we'll take our work, which is 300 times 10 to the 3. We'll divide it by our time, which is 3.2. And that will give us the average power. So again, stick that on your calculator. Feel free to pause this video anytime. And we'll get an answer of 93,750 times 10 to the 3. Oh no. 93.75 times 10 to the 3 watts. Okay, so that's our average. Now let's go for our max power, which is a different formula, Fe. So again, just come back, we've got 2000, or 2 times 10 to the 3, we're writing it a couple of different ways, times velocity, so it's a velocity in meters per second there. That's 27.7. So 2000 times 27.7 equal, and we'll get 55.4 times 10 to the 3 watts. Okay, now there's this phrase, this word up here, dissipated. Now what that actually means is the power lost. Alright, so as you going into this pit lane, you have to lose power so you can slow down. And we can see here, we've got the average power that we've lost during that time is 93.75 times 10 to the 3 watts. But the max power is 55.4 times 10 to the 3 watts. So a couple of different answers there. But depending on the question, it will determine what one of those you're going to use. Let's do another one. So hydraulic ram exerts a force of 250 newtons to move an object through a horizontal distance of 650 millimeters at a steady speed. If the operation takes 1.25 seconds, determine the velocity, the work done, and the power developed. Now if you have a little look here, you can see there's hydraulic rams here. That's a digger, and that's what a hydraulic ram would look like inside. So we're going to come back over, we'll have a little look through. So we'll list the values. We'll do F equal 250 newtons. We've got a distance of 650 millimeters. So distance 650 millimeters. Now don't forget, we have to divide that by 1,000 to turn it into meters. Always meters for these calculations, boys and girls. Last bit of information we've got here is time. So time is equal to 1.25 seconds. So first thing we're going to do, we're going to calculate our velocity. It's asking us to do that. Now again, if you've forgotten how to do this, go back to the previous videos in the dynamics playlist, and what we'll have is we've got velocity is equal to distance divided by time. So we'll go velocity, distance we've got 0.65 divided by time, 1.25. Again, pop that in your calculator. So we'll get a velocity of 0.52 meters per second. Okay, now to find out the work done, we don't actually need this velocity, but we can use that a bit later when we're talking about power developed. So let's go for work done there. So we'll do work is equal to force times distance. So we've got force is 250 times 0.65. Again, stick in your calculator. And we should get an answer of 162.5 joules. Power developed, we'll just do the average power. So we'll do the average calculation is equal to work divided by time. So the work 162.5 divided by time 1.25. And we'll get 130 watts as our answer. Okay, so we were tapping into some of our previous dynamics knowledge there by being able to calculate velocity. Now obviously if I wanted to calculate my max power, I could use my power max. Oops. It's FV, because I've got my F and I've got my V. I'll let you have a little go at that one. But that's a sort of brief run through of working power, and hopefully you'll be able to have a little go at these questions. For those of you who have got a workbook, they're in there. I've also put them on Canvas, but if you can obviously just pause this video and have a little go. So make sure you have a crack at least the first 5 of these. They get a little bit trickier as they work their way through, but if you can do the first set, then I'm pretty sure you'll be on the right track. But once again, thanks for watching, and obviously if in doubt, give me a shout and I'll help you as much as I can. All the best, bye bye.